hi to everyone around the country and welcome to today's seminar. First, I'd like to take a moment to acknowledge the traditional owners and the custodianship of the lands on which we meet today. I pay our respect to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australia and global society. I just wanted to briefly introduce myself. I'm Rennie Lee. I'm one of the co-conveners of the LCC seminar series. So this is actually our first seminar for 2023. So I'm very excited to get started with you. Today, our presentation will be presented by Ruihong and his work with Professor Helen Huang. So Ruihong is a Life Course Center Research Fellow here at the University of Queensland. So he has expertise in sequential modeling and has been actively engaged in cross-disciplinary projects. And the work he is presenting today is a collaboration between Professor Helen Huang's team, which she sits on, and Professor Simon Smith's team. And they're focusing on data science methods for driver drowsiness analysis. And just a short note about Professor Huang. She's one of the LCC chief investigators here at for the Life Course Center at the University of Queensland. And she's one of the discipline leaders for data science in the School of Information Technology and Electrical Engineering. And her research includes big data management, responsible data science, multimedia, and social data analysis and machine learning. So I think with that, I'll let Ruihong take over, and just wanted to give a warm welcome to Ruihong today on his presentation.
Today, our talk will be about how do neural networks analyze drowsiness level for drivers. This talk will be delivered by me, Ruihong, and Helen. So, firstly, I would like to acknowledge the country. So, the University of Queensland acknowledges the traditional owners and their custodianship of the lands on which we meet, and we pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. And today we're going to talk about road crash. So road crash itself is a threat. It is a threat to family and community. If the road crash happening, there will generally be devastating loss. And also this risk is increasing most severely in rural areas. And according to a recent statistics, we can see that the social cost. What is the social cost? We'll talk about a bit later. The social cost of the road crashes. It is a base case estimate of about 27 billion annually between the years from 2016 to 2020 in Australia. So what is the social cost? For example, you may need to pay a cost, and you may need to pay for the workplace or household losses. And all of this costs together, it is a big number. So road crash itself is a big threat to the society. So whether we can prevent road crash, there are many policies that are already being deployed to prevent road crash. For example, we can see there are many speed cameras on the road. And we can also see there are some policy about regulated work hours for drivers, or we even can see that there are some fatigue management for taxi. So there are many existing policies, but these policies are exerted by the policy makers to the most of the drivers. So we are asking one question. So can we tell the drowsy driver if a driver is drowsy? It is dangerous now, so we need to stop at the moment. So we're asking this question: can we tell them? And so to tackle this problem, we form a team between ITW Data Science at UQ and the Social Science at UQ, and also the UQ AI Collaboratory. With the team, we have a lot of names here. So the outline for today's talk will be in 4 parts. The first part will go to a simplified machine learning part. So I want to bring all of us together into the same language about machine learning. So for machine learning, we firstly will think of there is a model for machine learning, and the model is generally a function. For example, y equals fx, and x here is an input, and y is the output. Then f is the function, this function has so many parameters, and this function can calculate y based on the x as input. And the parameters in f needs to be optimized. So this is what a general machine learning model, it is just a function. Given some input, then we can calculate some output. And then how do we optimize these parameters? We will have a data set. We call it a training data set. For example, this data set includes a lot of x and y. This kind of x and y is correct. For example, we call it x train 1. This x train 1 could be a image of cat. And then the y train 1 will be the concept of cat. And x train 2 will be another image of cat, while the y train 2 is still the concept of cats. We have a lot of these different images for cats and dogs and horses, koalas, etc. So this is our training data set. We have the input x, different input x, and then their correct y. We call it the label, the correct y. So when we have this existing data set, we want to use this data set to optimize the f that has so many parameters to be the f asterisk, which means that it's a optimized f. And when we successfully optimize the f, we want to test this f asterisk whether it works for real situation. So in this scenario, we'll have a testing data set. Testing data set means that, okay, we'll have a lot of more x, which means we'll have a lot of more different images of cats. And then we want to predict, okay, is this image a cat or is this image a dog? This is a very common example in machine learning. So machine learning model, we have a function, and then we have a correctly labeled training data set to optimize the function f. And then when we optimize the function successfully, we want to test this function with another data set to see whether it works. So what is a simplified deep learning? So deep learning is basically doing some very similar thing to machine learning. So we can see that there is still a function f, and it has so many parameters as well. And then given an image or given an input, we want to calculate some output. For example, given an image of the character A, we want to say that, okay, this is a character A, the concept of A. Deep learning is something that we generally hear about, maybe, for example, neural networks. So for neural networks in biology, something looks like this. But in computer science or in data science, when we talk about deep learning, it's generally a calculation unit. Oh, that means it has a lot of inputs together, and then do some linear calculation, the so-called activation non-linear calculation, and then we get another set of output. So basically, it's just a more complicated computation unit compared with traditional machine learning. So we look into an example of deep learning. So still we have a input of image A, and then we have output which we want to predict, okay, what this image is. And then where is the deep learning happening? So it's here. We have a lot of calculation units in between. So each layer, it consists of so many computation units. So it makes the deep learning model very complicated. This is what a simplified description of deep learning. So basically, it's still a function, and then this function still have so many parameters between the input and output. And the final task of this function is just to calculate an output based on the input. So this is what a simplified description of machine learning and deep learning. So when we are talking about how do we collaborate with other teams to working on a data science method for the domain tasks, we generally have a pipeline of how do we collaborate together. So this pipeline is something like this. Okay, the first question is that within the domain, what is a meaningful or what is a reasonable task? So this is the first thing that we want to do. We firstly need to identify a meaningful task. And the second thing is that we need to identify whether we can have the data. So if we can have the training data set, which consists of the input X and a correct label Y, then we can try to use this training data set to optimize the function that can perform the task that we identify in the first question here. And the third thing is that we have a lot of tasks, a lot of technologies, and then these technologies are the last thing that we will be concerned about. So we will have a lot of choices of the technology, for example, machine learning models, deep learning models, or even statistical models. So this is a general pipeline of how do we collaborate with our partners. So when we are talking about collaborations, we generally will ask another questions. So how to apply this machine learning techniques for this drowsiness study? So that we will have a lot of questions in the later slides, and then we can see how do we deal with them. So this question may include, for example, how to identify the limitations of existing machine learning models, or how do we handle potential issues, or how do we design more effective models or strategies to apply these machine learning techniques for our study. So we'll now talk about the exact project that we did during this collaboration work. So the first thing is that if we want to tell the driver it's drowsy, we need to tell them when they are drowsy, we need to stop. It's dangerous now. So the first thing is that we need to tell the driver when they are drowsy. But when exactly is the driver drowsy? This is something that we don't know. For example, are they just yawning, or are they just rubbing their eyes, or are they just blinking? When these things happen, does it mean that the driver is drowsy? Or even at night, when the driver is driving within the car, when it's at night, whether we can see these situations. So there are so many factors that we need to be concerned about. Is it objective? Is it accurate? Or is it even too late for us to tell when the driver is drowsy? So in this project, we rely on a mathematical metric to determine the drowsiness level of a driver. So this mathematical metric is based on the wake-sleep model developed by Professor Simon Smith's team. This metric is based on the EEG signal. EEG signal is a signal that comes from the brain. So in the lab, Professor Simon's team, they collect the EEG signal, and then they use a model to mathematically measure the drowsiness level of a person. So we rely on this metric for the drowsiness level measurement. It is accurate and objective because it's based on the signal, based on the brain signal. But the question is, can we tell it earlier, during driving? This is a hard question because all of these signals are from the lab devices. But we want to tell it when the driver is driving. So this is a hard question because we don't have this kind of devices during the driving. So the task is something like this. Okay, so we now want to build a function that performs y equals fx. The y is the measurement of the drowsiness level. Then we will have a lot of machine learning models, deep learning models. All of them are for the f. But the question now becomes, what is x? That means, what is the input? Or the other question is, based on what factors we can tell what is the drowsiness level of a driver? Is it just the behaviors of the driver? For example, the yawning, the blinking, the rubbing eyes, or is it the driving patterns, or other factors? In this work, we rely on something called habit. So there is already preliminary and empirical observation on the relationship between habit and drowsiness level, which means there are some certain statistical relationship between the habit and drowsiness level. It means that we can try to use habit as input to kind of correlate the drowsiness level given this habit input. The merit of using habit is that the habit is easy to measure in lab using another kind of devices. and they will generate ECG signal. These signals can tell the heartbeat as data. And then the heartbeat is also easy to measure during driving. For example, we can just measure the heartbeat, just use the smartwatch wristband. I think people have experience about using for example, the Apple Watch. They know that there is a ECG choice that can tell them the heartbeat data. So heartbeat itself is easy to measure in both lab and in driving scenario. Now we also know that the heartbeat is also kind of correlated to the drowsiness level. So in this work, we want to try to build such a correlation between the heartbeat and the drowsiness level. If we look into the data that we collect inside the lab, it's something like this. The yellow line here is the mathematical metric for the drowsiness level developed by Professor Simon Smith's team. So it's basically a 0 to 1 value. This value, when it's closer to 0, then it means the person is drowsy. If it's closer to 1, then means a person is alert. And then the purple line here, it means the heartbeat data collected by the ECG signal from the lab. So which means that we want to use the purple line here to predict the yellow line. This is a simple description of our project. We want to use the purple line here to predict the yellow line. So the pipeline here, it becomes, we want to predict whether a person is drowsy, given the heartbeat data, no matter this data is from wrist or from ECG. And then the second step is that we now need to prepare the data set to train the function that we identify in this first step. The data set needs to be including a lot of X and Y. X here means heartbeat, and Y here means the drowsiness level. And then we want to use the lab data collected inside the lab for the training data set. And then we want to use this data set to build a machine learning model. And then we want to optimize this machine learning model based on this data set that we collect. And then we expect that the machine learning model that we built can predict whether a person is drowsy. This is what the task that we identify inside this collaboration. So if we look into the data again, it's something like this. The raw data is something like this. The purple line, it means the heartbeat data, and the yellow line, it means the drowsiness level. We want to use the purple line to predict the yellow line. And then during this data collection procedure within the lab, the participant will go through a period. It means the main drive period. This main drive period means that the participant is doing a monitored driving experience within the lab. And then we plug all the devices on to measure for example, the ECG signal for the heartbeat, and then the EEG signal for the drowsiness level. We measure this signals when the participant is doing their simulation driving. So if we look into this area about when the participant is driving in a simulator, it looks like this. It's a bit cleaner compared with the figure that we see in the previous slide. It's still the purple line for the heartbeat, and then it's still about the yellow line for the drowsiness level. Again, we want to restrict the data that we look into to this specific period for the participant just doing their driving simulation. So what are the green dots here? The green dot here means the peak. What is the peak of the heartbeat data? That means the heartbeat, the moment that the heartbeat. So this is what we look into carefully or zoom in the data. So this purple line is the heartbeat data. It's a signal like this, a little bit noisy, and then it gets a heartbeat. And then the first step is that we want to know where is the beat. This green dot means that it is a beat. It is a heartbeat. So the first step is that we identify where is the heartbeat. And there are also some very noisy data. For example, the red dot here means that these are not the beats. we can see from the left figure here, this participant, the data for this participant includes a lot of non-bit. So this is, we think that anomaly for our data set, it's not for the health situation for the participant, it's just for our data set. So this is an anomaly. In this situation, we can hardly use the data, so we'll just remove this data, because when we look into zooming the data, it's something like this, which is very, very noisy, and it looks very abnormal. So after we remove this abnormal data, we'll have something like this. We have the task now. The task is to do y equals fx again. And the y is the drowsiness level. We identify, okay, we want to predict the drowsiness level in the next 5 seconds, given the current input. Okay, so we want to predict the drowsiness level in the next 5 seconds. So when we say given the current input, what do we mean current? So we want to make it a little bit shorter. So we just look into the previous 30 seconds. So it means that we want to use the previous 30 seconds, the data of the heartbeat, to predict the drowsiness level in the next 5 seconds. So for simplicity, we don't exactly using a 30 seconds. Instead, we use beats. So the task, it changes into, okay, we want to tell the drowsiness level in the next 5 beats. And then we want to use the previous 30 beats of the heartbeat in the history to predict the next 5 beats. So this becomes our exact problem for our data. So we want to use the previous 30 beats of heartbeat to predict the drowsiness level in the next 5 beats. This is what our task is now. So when we after we look into the data with some detected green dots as peaks and then some red dots as non-peaks, we have some thoughts that if we want to use the heartbeat as a input that can work in many situations, then we may not rely on the heartbeat itself, the strength of the heartbeat, because for different devices, the strength of the heartbeat will be different. For example, for the smart watch or for the wristband, the strength of the heartbeat is a bit different from the ECG that we collect from the lab using the ECG signal. So we want to rely on the interval of the heartbeat. That means the gap between the consecutive 2 beats. So this we call it HRV, the heart rate variability, or we call it R interval. So this means that it means the rate of our heartbeat. And then we also use the 1 order difference of this R interval, which means that whether our heartbeat is changing, it's becoming faster, or whether it's becoming slower. Then after we kind of process the original heartbeat data into these 2 features, the first one is the interval between each heartbeat, and the second one is the interval of the interval. So we call it a 1 order difference of the R interval. So the red line here, we are still looking at the period that about the main drive of the participant. So in this figure, we no longer see the purple line about the original heartbeat, but we see the red lines here. It means the R interval, the heart rate. So it's approximately between 0.5 and 1.0. It's a bit faster than 60 beats per minute. And then we also have the blue line here. It means the 1 order difference of this R interval between of them. So we can see that, okay, this blue line is kind of around 0 because a human's heartbeat is relatively stable. It may become a little bit faster, a little bit slower, but generally it's around 0. So now the task it becomes, we want to use the red line and the blue line together to predict the yellow line. this is what our final task becomes. So after we process the data, we have a statistics of what this data set looks like. So from the left figure, it's a rejected rate. It means how the proportion of how many red dots we have. We can see that there are some participants that they have almost over 70% of the heartbeats are kind of hard to detect it. So it may be because of the collection procedure, or it may be because of the health situation that the participants' heartbeat is not easy to identify, not easy to detect. So we just remove the rejected peak ratio greater than 0.2, because in this situation there are just too many rejected peaks, undetected peaks, which makes us cannot have a consecutive 30 beats. If we remember, we want to use the previous 30 beats of heartbeat to predict the next 5 beats of the drowsiness level. It means that if there are too many rejected beats, we are hardly getting those consecutive 35 beats of the segments. So in this situation, these participants, the data from them are generally removed, or we skip them, and then we use those cleaner data. So when we do one more calculation, we count again. We count how many 35-second segments that we have for each participant. It's the histogram is something like this. There are way more behind here, and the mean number of segments is around a little bit more than 1,000 segments for each participant if we remove this abnormal data. So the number is fairly large if we talk about the big data. So this number of data, it's quite good, quite sufficient for us to build a machine learning model. So we do one more histogram to count the group of different drowsiness level. For example, here we set the bean interval to be 0.1. It means that, okay, the drowsiness level from 0.0 to 0.1, the percentage of these segments is about 44.8%. And then for the drowsiness level from 0.1 to 0.2, it's about 16.7%. So we count every bean with the interval of 0.1 in the drowsiness. And then we have these statistics. We can see that it's a bit unbalanced because we see a lot of data actually from 0.0 to 0.1. And at this moment, our team decided that, okay, we want to do this task in a preliminary way to see whether the model can do something to predict whether we can predict the person is drowsy if their drowsiness level is lower than 0.1, or the person is alert if their drowsiness level is greater than 0.1. So this is how we set the task now. We set the task into a classification problem with 2 classes. One class is the drowsy class. We call it class 0, with drowsiness level smaller than 0.1. And then we have another class, we call it alert class. This class has the drowsiness level greater than 0.1. So this becomes our prediction target. We want to do a classification. We want to classify whether a person is drowsy or not with the drowsiness level predicted less than 0.1 or greater than 0.1. So this is our final task. And then finally, we can come to the modeling part. As we talked about, we have a lot of different modeling techniques for machine learning, deep learning, statistical model. So in this task, we have chosen 4 different models. They're called multi-layer perceptron, and we call it MLP, or these 3, they are kind of recurrent structure. It means that they can inherently use the sequential patterns of the data. For example, it's called recurrent neural networks, RNN, or it's called gated recurrent units, or GRU, or we call it long short-term memory, LSTM. So basically, we have chosen 4 different models in our projects, in this project. And then the first one, this one, MLP, it's a model that it automatically flattens all the inputs and then put them all together at once into the model. So we can see that it puts all the input together into the model and then calculates an output. While for these later 3 models, they are a kind of a recurrent structure. It means that they will put the sequential input step by step into the model. So they are inherently sequential models. So the most important difference between this MLP model and the other 3 is that whether we explicitly using the sequential patterns of the data. So these 3, they are using the sequential patterns. And this one, they just flatten all the inputs and put them all together at once into the model. So we have 4 models for our task. So we have a table for the performance of these 4 different models. So firstly, we can see there are 5 metrics to verify how well these models perform. So when there is an upward arrow, it means that for this metric, the higher the better. When there is a downward arrow, it means that for this metric, the smaller the better. So we see this matrix here, the green, the red. So for our project, we want to say that the positive class, it's the alert class, and then the negative class is the the positive class is the drowsy class, and the negative class is the alert class. So true positive, false negative. For example, for true positive, it means that okay, the ground truth is drowsy, and then we predict this data as drowsy. And for this false negative, it means that the ground truth is drowsy, but we predict it as alert, then it's an error. So for this true negative, it means that the data itself is alert, and then we predict it as alert. While for the false positive, the data itself is alert, but we predict it as drowsy. So this is what this matrix stands for. So what I want to try to do here is that we have this kind of the metrics. For example, the precision one, it's calculating the ratio between the true positive, which is the drowsy data predicted as drowsy, compared with the alert data predicted as drowsy. So this precision matrix is calculating this part. They're seeing the ratio between this cell and this cell. And the recall is doing this thing, but vertically. They're looking into the drowsy data, but with the drowsy data, whether it's predicted drowsy or alert. And then we also have the this accuracy. So accuracy, they case all these 4 cells here. So, and then we still have the F1 score. F1 score is a kind of mean. We can just simply think of it as a mean between precision and recall. While the loss is the objective function that we want to say, okay, whether the loss, we call it cross entropy in deep learning. It's something that to measure whether the model is performing good or bad. So we have these 5 different metrics. And then we can firstly see that, okay, for MLP, which doesn't use the sequential data, the sequential patterns explicitly, it's actually not performing too good compared with other models. We can see that, for example, for F1 score, all other models they have higher performance. For accuracy, all other models have higher performance. So this is because the model itself is not explicitly using the pattern, the sequential pattern. While for these recurrent structures, we can see that, okay, they basically have a better performance compared with MLP. And then we also see that, okay, for although all of these 3, the INN, STM, GRU, they are recurrent structure, they still have some performance difference. Maybe because their model difference. So we can see that, okay, although GRU and STM are quite similar, but they still have a almost 0.1 difference in their accuracy. And also have this confusion matrix we just choose two models to talk about here. One is the MLP, the other one is the best performed GRU. So we can see that because when we do the split of class 0 and class 1, we see the percentages is about 44%, 45% to the other 55%. So the data is kind of balanced in terms of the class. So we see the prediction itself is quite balanced, although they will have difference in their performance. So GRU is basically better in both the drowsy class and the alert class compared with MLP. We see the GRU has a higher performance here. And when we look into the prediction score, we can see that the GRU in this figure, the x-axis here, it means the true drowsiness, the ground truth, and the y-axis is the predicted score. So we can see that for GRU compared with MLP, for this when the data's ground truth is drowsy, we predict this data closer to drowsy. And when we have the data closer to alert class, which means that it should be higher than 0.1, we predict them closer to 1.0 for this yellow dots. But sometimes we see that, okay, the GRU is kind of overconfident. What do we mean by overconfident? For example, although some of the data, their ground truth lies in this gap between 0.0 and 0.1, which means that they are drowsy. But the model sometimes will predict them very confidently to 1.0, which means that the model thinks that, okay, this data is very alert. So we can see that there is a potential harm of simply using this kind of machine learning model, because sometimes they will be just wrong, confidently wrong. So this is a question that we will think about in the future. And if we look into all of these different models, we will have different model prediction patterns for all of them. So we'll just skip this. And we actually do a lot of experiments. We can see, for example, for different models, we have different choice of these choice of models. For example, the learning rates, or the size of the model, or how many layers of the neural network. So we did a lot of experiments, and actually we care more about the performance finally. So we need to do a lot of tuning of the model, and sometimes we can see that some models are not performing well. They're ranging from 0.9 to 0.6, but some of them are quite better, from 0.94 to 0.72. So we need to choose carefully, and we need to do a large scale of experiments. So for future work, we firstly say that, okay, well, we can try to train our model with a cohort, and then we test the model with another cohort. This is a quite common thinking. So because we can actually recruit everyone to our lab and help them to identify their driving patterns, or whether they're drowsy or not. So this is hard. So we want to say that, okay, whether we can train our model with a cohort, and then we test the model with another cohort. So the performance now is actually a little bit bad. It's like just random guessing around 0.5. So we may need to identify more useful inputs, and we want to have some more generalizable input that can be used across different cohorts. And we can see this prediction behavior is kind of weird. Sometimes it's predicting quite randomly around 0.5, just random guessing. But sometimes it's guessing confidently wrong. Everything is wrong, and then it still goes back into the prediction is around, the accuracy is around 0.5. So we still have a lot of to do to look into what kind of features is useful, or whether this task is actually doable for different cohort. And a second feature work is that we want to maybe want to use different data source. For example, Now we are all using the data collected from the lab using the heartbeat data is collected by ECG. What if we really want to use a smartwatch? Then there's another task. For example, the lab figures, these two figures are from the lab with the ECG signals. Then right, these are from the Apple Watch exactly by our lab. So different data. So they look kind of different. So we need to test them. We need to see whether they have potential in transferring the knowledge learned by the model between different data sources. And also we may want to try to see whether we can use shorter input for a longer prediction. This is sort of a future task. So the final page about this talk is that we want to apply AI machine learning techniques. So there are still many questions, and when there's question, we see potentials. So the first thing is that we want to see whether there's data. So because data is not always available, whether we can collect them on purpose, or whether we can just use them publicly, or whether it's a already existing data set. So first thing is that we want to have data. And the second thing is that this solution is not always straightforward. For example, in our future work part, we say that, okay, if we use the same techniques, maybe it works in one scenario, but it won't work in another scenario. So we need to do some more jobs or works to identify, okay, how we can achieve what we want to achieve. And the last thing is that this machine learning model is not always off-the-shelf tools. That means we can't just grab them somewhere else and then plug and play. It's not always this case. So we need to do everything carefully. We need to identify the task. We need to see what the data looks like, and then we want to build our model carefully. So these are the references for today's talk. And thanks everyone. Thanks. Question are welcome. Thank you.
Thank you very much for this fascinating presentation, which is very much of my own interest. So I wanted to know, what was your rationale for selecting your cutoff for identifying drowsiness from alert state? If you go back to your slide that you showed us, about 45% of people were drowsy and the rest were alert. Yes. What was your rationale for that? Was that only because like almost half of people were drowsy? That's why you chose that point 1 as a cutoff?
Yeah, so thank you for the question. I think the question is about what's the rationale of choosing the splits here at point 1. Yeah, so I think the answer is twofold. So the first one is that based on the wake sleep model developed by by Professor Simon Smith's team, so they told us that, okay, it's kind of rational to set the splits somewhere between 0.0 and 0.4. So it's not exactly accurate to say it. So, but there is not an absolute threshold. So they told us that, okay, it's rational to set the splits between 0.0 and 0.4. And the second factor is that, okay, it's just as what you say. We want to firstly to see when the data set is kind of balanced. By balance, we want to say that, okay, we have 50% for this part, almost 50% for the other part. So we want to see whether the model can handle this kind of initial, preliminary, relatively simple case first. So this, I guess it's the question, it's two both first. Firstly, it's the rationale from sleep study, and the second thing is the rationale from the data science perspective.
Thank you.
Thank you.
And the other question is, have you just anticipated your performance of your models against the short-term alertness in drivers? For example, a driver is driving, something is just popping up in front of the driver, and that increases their heartbeat quite a lot for short term, and then heartbeat returns to the drowsy level again. So is your model capable of anticipating that fluctuation, or that might cause a problem for your model?
Thank you. I think the question is whether our model can handle the sudden fluctuation because of the outer environment's change. Is it a question?
Yes.
Yes. So I think this is a good question that we for this question, I think we need to look at we call it data distribution. So in the lab scenario, sometimes in the driving simulator, they will pop up some rocks or something and they can obstruct the road. And then in that scenario, we actually can collect the data of those scenarios. When something pop up, whether the driver will become suddenly, the heartbeat become a little bit faster. When the data can cover those scenarios, I guess the model can try to learn those scenarios. But when, so I think it majorly falls back into whether we can have those data. The data.
Okay. So just a note on that. I developed scenarios. I'm from the Professor Smith's group and developed those scenarios myself. And I haven't input any kind of those kind of fluctuations in the scenarios. So there is unlikely that something pops up in front of the driver. So you wouldn't have necessarily those data in your model. So that's something that should be considered.
Yes, I agree.
Thank you.
Thank you.
So there's a question from Mark Stevenson in the chat, and I'm not sure. Let's see if Mark is here, but he had a few questions related to heartbeat. Oh yeah, I see Mark in the chat. Did you want to ask your questions, Mark?
Yeah. Can you hear me now?
Yeah, clearly.
Oh, great. Look, terrific presentation. And I think the important point out of this that I'm taking is just some of the approaches you're using in relation to machine learning. But the challenge you've got as well is that you're training the model on data that is, in essence, a subset of really drowsy drivers, and your predictions are they're okay, but they're not great. And I think your point you've highlighted here is, for this to be really successful in terms of alerting a driver to being drowsy and to avert that sort of behavior, I mean, we're going to have to get this machine learning operating at our level across the population. And so, the take-home message I get from this is your data, you need different data to train in order to get very sensitive results. And I question then that the heartbeat is the one that you should be using. And the reason I'm saying that is that we've been doing the same as this, and we actually now have a commercial product linking this, but we've used the actual big data that comes from the car itself, and we've trained it on visual data that captures whether the driver's asleep or dozing or has eyelid closure and everything else. And on that basis, we get very, very good predictions, up around 98% across a whole population. Because the challenge here as well is some of the aberrant heartbeats that you're getting as well, you exclude from the analysis as well. And the reality is this has got to be a tool that operates across the entire population. Everyone's driving as such, and so it would be very valuable. And so you do need to also be able to ensure that you have those aberrations in there and that it gets picked up as a false positive and excluded. So I think that was the point, that it would be useful. I like what you've presented in terms of what are the more robust methods that you can use. But I think spending a lot of time just on the heartbeat, I think, is a real challenge. And I think that there is operation that we can certainly collaborate with sort of the data that we've got, which will give you much more sensitive information.
Thank you, Mark. I think this is a very, very good point. I think Mark's gonna bring up the discussion about what actually is what is the input to predict whether a driver is drowsy. So in Mark's example, in their work, they choose to use the driver behavior, and in our work, we want to try to use the heartbeat. And these are two different choices of input, but I think they are very kind of promising in the future. So I think in this work, we want to see the potential of using heartbeat purely instead of using those computer vision techniques, using the driver behavior captured by a camera. So we also list out of them, whether it's a behavior or driving patterns. So I think as much as I think we can have a very promising collaboration direction if we can use both or all of these different sources of data, for example, the driver behavior or even the movements of the car or the trucks and the body situation, for example, the heartbeat together, we can try to make a more robust model as Mark proposed here. Thank you.
This might be a dumb question, but I'll ask it anyway, because I mean, these models are, they're hard for me to get my head around, although I think I understand the kind of overall logic, but obviously not the detail. But I'm wondering, Ruihong and Helen, or even Mark and others who've used these models, and this must have been done, right? There must be analyses that show that these models are better than, regular statistical regression models or, other kinds of models that we would normally use on, sample data. And I'm just wondering, have you done that, or are there papers that we could read that kind of show how machine learning models, really add to, these other more basic, models that we're more familiar with, or at least I'm more familiar with?
Thank you, Jenny, for the question. And I think Jenny's question is about maybe we have some we call it traditional method like linear regression or statistical regression models. So, and we also bring up machine learning model. We call it deep learning models here. So, do we have comparison, or do we have any discussion about which is better, which is good, which is bad? Are they related or something? Oh, sorry. So, we do have this kind of comparison. So actually for this multi-layer perceptron model, it actually looks like a linear regression that we look in the statistical method. So as like we say that it actually flattens all the input and put them all together into the model, and then they have different weights and they have different weighted sum. So actually it looks like kind of a bit complicated linear regression. So I think this can kind of answer the question that whether we compare the machine learning or deep learning models with the traditional regression model. Is it good for the question? Yeah, thank you.
So I'll just read Simon's comment, which was, I think it was more of just a comment kind of in regards to Mark's last comment, which is he's saying that, yes, I think heartbeats are not perfect for driving, but they're interested in other cases of vulnerability from fatigue, i.e. all sort of precarious work, algorithmic management, unregulated work where mass data may become available. Okay, so if there are no other questions or comments, then I just want to say thank you to Ruihong and Helen for a great presentation. I think we all sort of learned a lot from it. And I know that a lot of people that are interested in kind of big data and kind of working with this. So I think this is a great, presentation for our LCC and kind of to get the audience kind of more engaged to it as well. All right, so I guess with that, I'll just say thank you again. And if everyone can, for our next kind of seminars, we have been watch out for the Source newsletter, which has information about our upcoming seminars. And so if any of you also are interested in presenting, feel free to reach out to myself or Nancy Call, who's the other LCC seminar convener. So thank you again, and I'll see you all soon.